Testing, testing, 1, 2, 3. Oh. There, I forgot my face light, so you can see my face. Okay. Hello, how's it going? Welcome to yet another edition of this course that you're taking this summer. Whoa, I've got that coming over my phone. Good show. So, Nick W., what is the most wonderful programming language that you found the other day, and was it Haskell? That's funny. Way to go, Konstantinos. That is excellent. Now that you speak binary, you can have lots of fun with all the rest of the nerds who also speak binary. So, I just wanted to commence our discussion of things tonight with some housekeeping detail. Wow, my forehead is so shiny. Good lord. I'm not going to start powdering my face. I'm not going to do it. That's something my brother would do. If you're watching, hi, Ben. Oh, okay. Oh, yeah, okay. You're talking about the one with all the arrows. See, that's all you had to say. I know which one you're talking about. I'm pretty sure that I can't say it either, because it involves the F word, I think. If it's the one I think the one that I'm thinking about. But yeah, that should be enough clues for anybody who's... Oh! There we go. Yes. Thank you. Yeah, that's an interesting one. It's almost more of a puzzle than a language. I've never really attempted anything with it myself. But anyway, so the thing that I wanted to talk about today is the test and how the test went. Yay! Because we had the test last weekend, and it would be good to have a discussion of it now that I have received the grades, and hopefully you will have as well. So, generally speaking, the grades seemed pretty high, and I was pleased, because I did not consider the test to be an overly easy test. It was testing some of the finer points of the things that we were talking about. It was, I think, a reasonable length for a test like that, and so I am inclined to view the good performance of the class on the test as being in some way correlated to you guys having absorbed some of the material, rather than me not being able to write a test. So, yeah, so I have some questions. Here are the statistics. So we had a average of nearly 90%, which is quite high. Not quite as high as midterm 1 from last semester, but that is an anomaly that you should go ask people you might know about. It'll be a fun story, a fun thing to chat about. I'm not going to say it. So the average was nearly 90%. Seems a lot of people got, like, in the realm of the maximum grade, if not quite the maximum grade. A lot of people got over 100%, which means that, people did pretty well overall. Hardly anybody failed. And, of course, these people at 0 are probably people who just didn't submit or submitted nothing. Yes, so Darth Binks says the test was very fair. I aim for fairness. I think unfair tests are not the preferable ways to go about testing people. But if I could get some idea from you guys, how long did it actually take you to write the test? Anybody who is, willing to share that information on chat, if you wouldn't mind. I always like to, it's kind of tricky to gauge test length. That's like the most tricky thing, because it's so variable between people. But if you wouldn't mind in chat letting me know how long it took you guys to complete the test, that might help me calibrate a little bit for the next one. And the Conway question was essentially a bunch of if statements, right? But just goes to show you, a bunch of if statements can be, still a sufficiently difficult thing to actually try to do. Well, Mr. Minder, even though you had a rather long, it seems, amount of time. Oh, okay. So you took some breaks. That's good. It's good to take breaks if you're doing anything for like 7 to 8 hours. Well, this doesn't seem to be too bad. Well, okay. So we seem to be having a range of responses, sort of people in the sort of 2 to 3 hour range, maybe 2 to 3 to 4 hour range, and then a couple of people higher than that. Yeah, okay. Like, the intention is that it's not although you have to complete it in one day, like, the intention is not for it to be, like, a completely time-limited test, right? But anyway, okay. I have acquired some interesting information. Good. So to the comment that the game of life question should have been a bonus question. In terms of difficulty, I agree. However, it kind of doesn't work out necessarily for the purposes of the grading scheme. Like, I don't want the bonus grade, like the bonus grade ratio, to be too high, because that kind of, you shouldn't have more than 15% of the grade necessarily be comprised of. You shouldn't be able to get more than 15% bonus grade necessarily, but yeah, I've done more than that in the past. It would have messed the ratios up quite a bit if the Conway question had been a bonus question, despite the fact that it was suitably difficult to be a bonus question. But a lot of it was knowing what to search for and how to apply it. Yes, that's kind of life itself to a certain degree. But, anyway, so that was the test. I tried to make it a little bit interesting, because, test questions can sometimes be a bit boring. But anyway, so that being talked about, I think we should probably move on to our lecture material for today. Oh, I might have a few more comments, though. Give me one moment. Oh, ouch. So with respect to the feedback, you should be able to pick up your feedback, should be able to fetch it through Jupyter. Even if you submitted through Avenue, you should be able to pick it up on Jupyter, because everything's run through the Jupyter server in order to auto-grade it, right? So if you're having any problems acquiring your feedback from any of the various things, please email Swale. He's in the TA list in the syllabus. He's the guy who's been looking after that kind of thing. So there was an experiment last week, one of those weeks, to try to upload those feedback HTML pages to Avenue as well, but I'm not sure if it actually worked out. Yes. Well, we will. The problem has been noted. I'll have a word with Swale about it. It seems like you guys haven't really been getting any assignment at all, any feedback for any assignments at all. So I'll have a word with Swale about that. If anybody has any other grievances, please let me know. Might as well get our grievances out. We'll have the traditional Festivus airing of grievances, which is a reference to Seinfeld, if anybody still watches Seinfeld. I have made a note. We'll figure something out. So, let's get into our topic of discussion for today. Today, we are going to be talking about testing and exceptions. So, testing is, generally speaking, the process of creating code which examines the correctness of code that's already been written, and exceptions are a thing that you should be familiar with by now. They are a mechanism that is employed by Python to denote when errors occur. By the end of lecture today, you will not only know how to deal with exceptions, but you'll know how to create exceptions your very own self. So, I have a question pertaining to the last lecture. For the binary square root search from last lecture, why did I set b is equal to 2 to the b? I used 10 to the b and it worked too. I don't really... if you could email me that question, I will answer it. I will answer it for you via email. It's sort of... I need to stay focused on our current lecture that we're doing. We are already 15 minutes into it after all. So, testing. Oh wait, whoa. These are the old slides. Oh no, I didn't upload them. Okay. Okay, I'm just going to pause. I'm going to hide the screen for a moment so I can log into a thing. Don't worry, I'm not gone away. I'm just, pay no attention to the little man behind the curtain whilst I acquire the slides that I specially commissioned TAs to create for me, so I should bloody use them. I am currently downloading the new slides. I am currently closing the old thing. There we go. Come on. So just a quick note to anybody who might be interested in doing any live streaming at any point in the future. Try to get any downloading that you might want to do done before you start up a live stream. That's just a better way of going about it. Open file. Open. Says me. There we go. Okay. returning to picture. There we go. All right. So, testing and exceptions. See, these are much better. So, here is a program. This program has a bug. Oh, yes. I'll do that during the break. So, we have a function, maxProduct, that takes as input a base 10 number s. Notice we're saying base 10 because we just had that lecture on things that aren't base 10. You can assume this is a decimal number, and outputs the product of the 12 adjacent digits that have the greatest product. So, imagine you have a string of 10 digits, or base 10 digits, right? You want to take a window, right? A window of adjacent digits. You want to measure all of these windows, what the product of all of the digits that are inside that window are, and you want to output whichever one is the greatest one of all the possible ones that exist in the string that you're operating on. So, we've got def max product. Our max product is 0. For I in range length of s, length of s minus 12, product is equal to 1. For j in range 12, product times equals s I plus j, the int interpretation of s I plus j. If the product is greater than the max product, then the max product is equal to this new product we've calculated. Return max product. So, what is our error? Indeed. What could it be? Does anybody in chat know what the error is? Let's see how long the latency is tonight. Tick tock, tick tock, tick tock. Okay. So, the problem is that we have an indexing problem here. So, if we take this code, yoink, and we load it up into something resembling a Python programming environment, and we attempt to run it on, say, some numbers, then we're supposed to indent things. Oh, that got like that. Okay. There we go. So, our max product is 12, 19, 27, 60, like that. However, just by examining this input that we've given it, we can determine, well, since this is an ascending list of values that repeats twice, if we check these numbers, right, those are going to be the highest numbers. We can even do this in a manner that makes it even more obvious, actually. So, if we run this, right, obviously the maximum product is going to be formed from the back end, right? However, is this actually true, right? Let's take a look. Calculator. Ta-da! So, if we 9 times 9, actually, you know what? Python is a calculator. 9 times 9 times 8 times 8 times 7 times 7 times 6 times 6 times 5 times 5 times 4 times 4. Is that 12 now? That's 12. Good. We can see that the actual result that we're supposed to get is significantly higher. This is interesting. So, what gives? Basically, the process that I've just illustrated to you is an encapsulation of all of the, like, your sort of regular testing program that you should run through. Your program as the programmer, so to speak. It's the routine that you should get used to and go through in order to determine bugs in programs and to see if there are bugs in programs. You take a test case for which you know what the correct answer should be. You run your code against that test case, and then you compare the results of the program to what you know the expected outcome should be. If there's a mismatch, then you know there's a bug. So the other thing that you can kind of do is you can kind of just calculate around and see if you can get the correct, if you can reproduce the error, right? So in this particular case, if I take 1 9 off the end and add a 3, basically that shifts the bracket down by 1. So we know that the program thinks that this is the bracket that contains the largest product, when in fact it's 1 over from that. This should indicate to the programmer that we are in the case of a off by 1 error, or an off by 1 error, because the thing that's being produced as the result is off by 1 from the thing that it should be. So the question then becomes, how? How is it being thrown off by 1? Well, you don't even necessarily need to know why, actually. It's useful to know why, because then if you know what the source of the problem is, then you can fix it and be sure of your fix. However, if you don't know what the source of the problem is, then you can just kind of start fiddling around with the code, see if you can get things to work. So, with an off by 1 error, generally speaking, that's caused by loop index variables being out of whack in some manner. So, because we're using for loops here, there's no explicit loop variable that's being carried through, right? In a while loop, you might have to worry about how it's being initialized and stuff like that. But since we're generating all of these values with range objects, all we need to be concerned with is, are these range objects receiving the correct information? So let's try this one. We're off by 1, so let's try 13. Does this do anything? Well, it makes us deviate substantially from what our expected result is, which I'm just reconstituting here. That's way too much, so that's bad. How about this one? That's way too little. So this seems like we're closer with this one for sure than we were with either one above or one lower. So it's entirely probable that J is not the problem. So let's try the other one. Let's try adding 1 to this. Oh, my goodness. So we know, since the outputs are now matching up, that adding adding 1 to the negative number, or decreasing the magnitude of the negative value that's being added to the length, or subtracting 1 from the offset that is being applied to the length. You know, all of those fancy ways of saying the things I just did numerically. This seems to have brought our algorithm in line with reality. So, we can often acquire this type of information by also using print statements, just to see what's going on. Let's restore it to its previous mode. So, we can see that I goes from 0 to 5 in this instance. So that means we are testing the first, second, third, fourth, fifth, and sixth value, right? So this, if we count forward from this last one, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, you can see that we should actually be going, we should also be testing the case where I is equal to 6, which would give us this interval, but we're not. The loop is ending too quickly. This is because there's been a misunderstanding between the programmer and the range function. Because if you guys remember, range gives you values up until the 1 minus whatever's provided to it as an argument, right? Like if we go range 12 and interpret that as a list, we get from 0 to 11. 12 objects in the array, but we're going from 0 to 11. So, if we take this into account, I goes to 6, and we get the correct answer. So there you go. We have debugged a program. And now we're going to go through like a whole butt-ton of slides that explain everything I just explained, but without the Jupyter interpreter. So there we go. How could we have detected this bug? How did we detect this bug? Number 1, make some test cases with known correct answers to see if we get the right answer. Selection of the test cases is key. There are people in this world, quite a few of them, whose job it is to create correct test cases. One of them is actually currently employed as a TA for this very course. I actually have a TA who a great deal of what he does is he designs the test cases for the tests and things like that. I won't give you his name because then he will probably get hate mail. Not that I don't trust you, I just don't trust all of you. Anyway, have another person independently implement the function and see if you both get the same answer. Possible, but labor intensive. Have another person read the code and see if they can find any flaws. Again, possible, but labor intensive and likely to fail. The easiest way to find what a problem in a program is to run a test case, or run several test cases. So, the goal of testing is to determine whether a program works as intended or not. Debugging is the process of trying to fix a program that you already know has a bug. These are key terms. There's this fun apocryphal story that's very popular, so a lot of people know it, about the origin of the term debugging, and I would be remiss if I did not relate it to you now, because part of my duty as your professor for an introductory computer science class is not just to teach you how to program, but to inculcate you into the culture of the computer programmer. So, this is the apocryphal story. way back in the olden times when people hadn't discovered the existence of solid-state electronics and everything still operated on relays and vacuum tubes, during the era of Casablanca, the movie, coming out, and Judy Garland, and the war had just finished, and all of these sorts of things. Back when newspapers were still a thing, and the way that you got the news, there were computers, but they were massive things because we hadn't discovered how to miniaturize them yet. So these complex pieces of electronic equipment would be the sizes of rooms, and you've probably heard this kind of thing before. It's quite fascinating to go back and look at pictures of old computers. But old computers had a problem. Not only was this prior to the invention of, solid-state electronics, this was also, in a lot of cases, prior to the widespread adoption of insulation on wires. So a lot of these things, the only thing that was insulating the wires from each other was air, right? So this is fine. But if anybody who's ever owned anything in a basement knows, one thing that is extremely attractive to things that are insects or even things that are small rodents is a closed-in space that's very convoluted where they can have their own little apartment buildings. And computers were such an object. So every once in a while, you had a computer that would have a mysterious malfunction. Nobody knew what the origin of the malfunction was. And the problem was, back in those days, you didn't have things like programmed computers, right? You weren't writing programs on a screen. You were putting a bunch of punch cards into a mainframe. So it turned out that more often than you would think, the problem that causes a computer error is some insect, a bug, like a moth or something, gets into the computer and shorts out a couple of the electrical contacts, and it gets fried onto the circuit, but it gets fried onto the circuit in such a manner that it's creating electrical contact between two lines that are not supposed to be, making electrical contact with each other. And as a result of that, you get these mysterious errors. So the process of debugging was very literally, you would crack open the chassis of the computer, you would go in there with a flashlight and a pair of tweezers, and maybe like a scrub brush, and hunt around for some bug or small mammal that had been electrocuted by the computer. And this term has passed into common usage among programmers everywhere. Debugging. This is how we fix computers. So, this is the cycle. This is the development cycle for your typical computer program. There are many, if you get into actual computer software project management and that type of thing, this will look very, very simplistic. But this is, generally speaking, how things go most of the time. First, you write your code. Next, you try to compile it. It has to be able to compile you have to be able to compile it to run it. Number 2, test it to determine if it works as intended. Number 3, you must identify the bugs if it does not operate as intended. Number 5, did I skip 4? Anyway, fix the bugs in the source code. So you go into the code, you say, oh, what's causing this particular malfunction? And then you fix it, and then you come back around and test it again. Never assume because you've modified the source code that you've fixed the bug. bugs can be tricky, and they can hang out in places that you don't expect. So you always have to verify to make sure that your fix has actually fixed the bug. Test early, test often. So there are a couple of types of testing methods that are used with respect to testing programs. Number 1, white box techniques. Number 2, black box techniques. So it's kind of a dumb way of saying it. In some sense, you should be more talking about clear box techniques and opaque box techniques, because it sort of relies on the idea of white and black denoting visibility, which they don't really, but, you know, it's the nomenclature. So what are you going to do? In white box techniques, you rely on knowing what the program's source code is in order to test it more effectively. In black box techniques, which incidentally are the preferred type of technique in most cases, you don't need to know what the program's source code looks like. All you are doing is you're commenting on the relationship between the inputs and the outputs. Right? So for a lot of functions, what the output should look like based on the input is something that is fixed. Right? That's something that's known. If you notice, when I make test questions for you, I'm always very careful, or at least I try to be, to phrase the questions in a black box manner. Given inputs this, that, and the other, produce output this other thing, which has X, Y, and Z properties. So this means that you don't need to implement it in a particular way. I don't need to know what your implementation is. All I care about is that if I give your program these inputs, it produces that output. This is, in fact, how the autograder even works. So both of these techniques require a clear specification of the program's expected behavior. So in order to define what correct functionality looks like with respect to a program, you have to know what that is, right? You have to know what is correct, what you consider correct, what you consider the correct output to be. Otherwise, how do you know if the program's fulfilling those expectations or not? This is a specification. A specification tells you how the program should behave given certain inputs. So, black box techniques do not rely on knowing the program's source code. They only rely on the ability to put an input in and see the corresponding output. And it focuses on the development of test cases to see if the actual output matches the expected output for each given input. So, again, test cases are a thing that requires skill to create. So, black box techniques are inextricably linked to a few of the software design principles that I've been trying to beat into your skulls over this very short number of weeks that we're trying to learn. We're trying to learn you guys programming. So, modularity and decomposition, right? We want to take our problem that we are applying a program to, break it down into easier to manage parts, ideally parts which can be reused, and we want to construct a correct solution to the problem from these broken down parts. And I know, like, to an extent, the tests, the assignments and the test haven't necessarily been asking you to decompose things, right? We're probably going to get more into that type of topic when we start talking about classes and object-oriented programming, which we are going to be talking about very shortly. Yes, sir, indeed. But modularity and decomposition. You want to break the thing down into constituent components. You want those components to be reasonably self-contained. They need to have a clear purpose, and they should be able to be reused. If you are writing functions, then you've achieved all of these things. So if you think about it, if you're taking a problem and you're trying to break it down into smaller parts, if you have a part that you have identified as a part of your solution, but it doesn't really do anything or contribute anything material to the solution, then what business does it have in your design? Absolutely none. So you should get rid of it if you're in that type of a situation. Maybe that little tiny small piece of functionality that you thought would be so well put in that particular module, maybe you can add that to some other module that does something similar. But the idea is, like the analogy, I think is kind of to something like a car engine, right? If you had to list out the number of parts that go into a car engine, it's probably in the hundreds at least for a modern car engine, and it depends on what you define as being the engine. If you're looking at just the stuff that's under your hood in a car, it's probably, 1,000 pieces or more. However, it won't be 1,000 unique pieces, right? It is if you count every screw, you're probably going to get a large number of different components. But hopefully, each screw, you'll have certain classes of screws, but you'll have exactly that. Many screws will be exactly the same part, and they will achieve the exact same purpose and be used in the same manner, just in a different part of the engine. This is how to think about modularity with respect to programs. Very engineering sort of way of thinking about it, and I realize this is a computer science class, but hey, I'm doing my PhD in software engineering, and you guys have to deal with it. But yeah, so that's sort of the way to think about it. Furthermore, we have the abstraction mechanism. The purpose of abstraction is to be able to use something without understanding it, essentially. So, I can say to everyone, oh, well, the way that a screw works is you take an inclined plane and you wrap it helically around a rod, and you taper the end so that it can enter some material with minimal force, and because the inclined plane does not sort of the channel cut by the inclined plane does not move relative to the thing you're screwing into, but the screw can move in that manner. You can push it to the point where it achieves enough friction to be able to hold the screw in place, and therefore your screw can fasten things together. You can say all of that stuff. That is a description of how a screw works, even if it's an imperfect one. But it's not necessary to understand the simple machine connotations of a screw to know that if you put it here and you take a screwdriver and you twist the screwdriver on top of it, that it's going to go into whatever you're trying to drive it into. You don't need to know that they were invented by Archimedes in order to be able to use them. This is the process of abstraction at work. Abstraction is it's one of the fundamental brain processes that allow human beings to interact with the world. And if you are designing good software, you are designing it in such a manner that the person who's using your function does not need to know how you wrote it in order to use it. All they need to know is what it does. So, modularity enables better black box testing. Obviously, if things are sectioned off into self-contained units and the purposes of those units are well defined, then you can test them with respect to black box testing very easily, because you can create test cases based on what the known ranges of what the known characteristics of the inputs are going to be, and what the relation of those inputs is to the outputs, which should be in whatever specification you're using. So we've got two different types of testing when we're talking about big programs. So big programs are programs that have a lot of different moving parts, so to speak. So if we go back to the car engine analogy, if you're testing the individual screws, or if you're testing a spark plug, for instance, that is unit testing, right? If you're testing overall the power output of the engine that you've constructed from the parts, that is integration testing. So in unit testing, you're testing the individual functions, the individual components, the individual modules, the individual classes maybe. And if you are testing at a top level a program that's made from all of these parts, then you are performing integration testing. And I have been known in the past to write test questions based on this vocabulary, because this is kind of a vocabulary slide set, this one. It's a vocabulary slide set, at least for the first half, and that's because the actual coding that's involved in this lecture is quite easy. Not that you heard it from me. So, regression testing. When a bug is fixed, and then later more source code changes are made, they might introduce that bug again, reintroduce it, re-expose it. Maybe the fix that you came up with wasn't really a fix per se, but was more of a kludge. Kludge incidents, that's another piece of programmer lingo. Kludge. The Wikipedia, I may have shown this already, but I don't care. The Wikipedia article for kludge has a fantastic photo of it, photo on it. Ooh, and that is also a good one. But here we go. See this? How the bridge collapsed and they just kind of built a new bridge over the old bridge? This is a kludge. You have not addressed the underlying problem. You have put the quote-unquote band-aid solution on it. So there you go. The problem with kludges and band-aid solutions, anybody who's ever observed the functioning of a modern government will realize that band-aid solutions become permanent solutions, because you just fix it and then you forget that you had to change that and it's working good enough, so there you go. Just don't change it until it breaks again. So that's why you want to address the underlying issues, generally speaking, if you can. So when you're developing a fix for a bug, you should always keep your test cases, and in particular, you should keep two test cases. One, a test case that'll fail if the bug is still there. So you need to have a test case that exposes the bug, and you need a test case that should pass if the bug is fixed. So you want to test not only you want to not only be able to reproduce the test, but you want to be able, or reproduce the bug, but you want to be able to tell when the bug is fixed. Using this method, you can test to see if your code has made a regression, that is, a going back to a previous state. So there you go, regression testing. And continuous integration testing. This is where you create an automated testing framework that runs all of your tests every time you make changes to the code, or when you upload them to some repository that your company or you may be using. Incidentally, if you have never heard of if you've never heard of a code repository before, these are like, they're kind of like meta. It's a piece of software that keeps an archive of the changes that you've been making to your software. So if you wanted to say, oh, you know what, I really hate all of the work that I've done on this since last Tuesday. I'd like to go back to the version of this I had on last Tuesday. As long as you uploaded last Tuesday's version to this repository server. Well, repositories can be servers, but they're not necessarily servers. You can have local repositories running on, operating on your system as well. You can do that. You can roll back to a previous iteration. That's sort of the classical example. Repositories, in the modern sense, allow branches to split off from projects. They allow a large number of people to be working on something simultaneously because it manages people. It allows us. It's a structured manner in which people interact with a code base, so that people don't like, oh, I'm just making some modifications to this, and like your buddy who you're working on the project with opened that file like 3 days ago and just never saved it, and then you make your modifications, and then they save their old version over your new version, and it completely blows out all of your changes. That kind of stuff can happen. That's real problems. That's real world problems. So repositories are meant to combat that sort of thing. And we're going to see a bit more about them after the break. See you folks in a few minutes. And I promise I will upload the new slide set. I did. I remembered. So, I brought the other kitten to say hello today. Hello. Oh. Say hello to the people in the say hello to the internet people. Oh, you don't wanna look at the laptop at all? Huh? Not even if I... There you go. Yeah, you're a good kitten. It's not easy being a new big brother with a little sister who just arrived and stealing all the attention and all that kind of stuff, you know. You got to make sure that your older children are still feel like they're loved. So anyway, you know, the whole whenever I bring a cat on camera, that's always a very popular thing, so I should probably keep doing that. So, here is an example of continuous integration testing. This is using the website GitHub. If you wish, actually GitHub was recently acquired by Microsoft, and I believe they now allow you to have private repositories for free. Correct me if I'm wrong on that, chat. But GitHub is one such repository. They will store files for you. You can collaborate with other people on coding projects. In fact, if any of you are people who are looking to get employed as programmers in your futures, it's actually a highly recommendable thing to have a few projects going on GitHub. You can have your GitHub linked to from your resume and stuff, and anybody who knows coding can look at your code and say, oh, this person's actually a fantastic programmer. Look how wonderful this code is. And then you're instantly hired. Just, you know, don't take my word on that, but yeah, that's generally speaking. Anyway, the point of this is that there's a module built in that automatically runs specific test cases on anything that gets uploaded to this repository. So, developing test cases. Generally speaking, you've got to think in terms of ranges of inputs. So, you want to think about the types of inputs that can be provided, right? In particular, you should pay special attention to what are called edge cases. So edge cases mean any case that takes into account the limits of a particular field of possible inputs. So if you think about, you know, is there going to be MS Paint Adventures again? I think so. If you think about an integer, right, as existing on a number line, right, in your code, certain things will happen based on integers being within certain ranges, right? If you have an if statement that says, you know, below 7 do something, above 11 do something else, right? These are, you know, this is the type of thing that happens in programs a lot. So, what you want to do is you want to have at least one test case in this realm, one test case in this realm, one test case in the middle, and you also want to make sure that you're testing the points at which the transition occurs. You want to test 7 and you want to test 11 in this case. Sometimes it can be as simple as you put a greater than when you meant to put a greater than equals to. That way the 7 would be included with this category of tests rather than that category of tests. You guys in chat are still alive, right? You guys have been, like, you haven't said anything for, like, nearly an hour. Maybe I should just reload. Maybe I'm just not getting Maybe I'm just not getting the chats. Oh my goodness. Yes, I have just not been getting the chats. Oh my goodness. Okay, I'm going to take a moment to review the chats to see if I missed a lot of... yes. Okay, so the updated slides are on Avenue. Yes, you are able to email me about the test after the lecture, but I probably won't answer till tomorrow morning because, you know, this lecture ends at 8:30. Yep. Yes. Yes, yes, yes. Yes. Yes, Basil's great. I agreed. Is debugging the 1940s equivalent of someone go jiggle the toilet handle? Well, in a sense, if the toilet handle was the size of an insect and located somewhere within, you know, what was probably the equivalent of a square mile of circuitry if you laid it out all flat. So yes. What's the best way to integrate previous projects into GitHub? It depends. It shouldn't, like, ordinarily it should be just reasonably easy, you know, make the README files that they want and then just copy and paste your source code. That will become like what you call an initial commit. It's actually pretty rare for someone to say, okay, guys, I'm going to bring this up straight from nothing in public view. Generally speaking, you have at least something before you announce a project on GitHub and, you know, start looking for collaborators or anything like that. No, I wasn't trying to speedrun the lecture. Yeah, my chat was dead for some reason. Good, good, good. I never miss a meme. Maybe I miss memes. Good question. Is next week's content going to be on the second test, Mr. Moore? Something about 1MD3. Yeah. Those are good videos. I like those ones. Not as much screaming or explosions, unfortunately. So next week's content, is it going to be on the test? Oh, wow. If I use my memory banks, we have tests every other weekend from starting from last weekend. So this weekend we have no test, but the following weekend we do have a test. And generally speaking, it is my policy that it is cruel and unusual to expect you guys to have absorbed the content from the lecture material that occurs the week that the test occurs. I just think that's cruel and unusual, so I don't do it generally. It, you know, kind of bogs things down a little bit with respect to the summer course because it's so abbreviated, and it means that the first time that you guys are going to be tested on the classes subject, which classes are like a huge subject that are occurring in the later like actually the next lecture is classes, and it's a really important topic, but you're not going to be tested on it until the exam, and maybe that's not a great thing because classes are a really important thing, but generally speaking, no. There are going to be three areas for the test next week. That is going to be the thing we're doing now, testing and exceptions, numerical methods and computations, and that other thing that we did. Just kidding. Functions and recursion. So there you go. Yes. So that should hopefully clear some brains with respect to what's going to be on the test. And it's kind of funny, like, I'm not saying Hey, Basil. Okay, everybody in chat, now is your opportunity to express your appreciation for Basil. He is an extremely awesome guy, and I'm very pleased to be working with him this semester. So, could we maybe have a practice quiz that's not worth any marks on classes at some point before the exam, just so we can see if we actually understand it? Yes, ask me about that again after I've written the test for next week. So, I don't want to discourage people from watching the lectures in the last week of classes, but there's a lecture there on machine learning, which we never get through completely anyways, and which I never really test on. And, I have been in the habit of doing some SQL stuff. Like last semester, I did some SQL stuff because that's interesting. But even that stuff that's like in the last week of classes, it's kind of it's sort of marginal material in terms of exam coverage, so don't worry about it too much. I will tell you what the major topics are. You don't have to try to intuit it from subtle hints and like subtle intonations of voice that I use during lecture. I will actually tell you what the major topics are. Just ask me. That being said, I haven't written it yet, so I don't know what's on it. So there you go. There we go. Basil, I hope that's enough love for you. He's been doing really great, though. I've been super impressed with how well Piazza is being looked after, and Basil is the man. He is the cheese. So there you go. Anyway, this other thing that I was talking about. So if you take a look at the if statement in which that makes this decision, am I going this way or am I going that way? Most probably you'll have something like a greater than. If you mistakenly put a greater than instead of a greater than or equals to, that means that this 7 will end up in the wrong camp, right? You can kind of imagine these corresponding to specific regions of outputs, right? So, so you want to test the 7. The 7 is the edge case. So this is reasonably easy if you're talking about integers. It's kind of obvious to see where the range is of an integer and the divisions that occur with that. But this is also true of list indexes. So similarly, I think I've got a slide on this actually. Yeah, so for max product, this thing that we did at the beginning, the problem occurred in an edge case, right? It occurred with the problem occurred when the correct answer was the last possible interval, right? So when you're designing your test cases and you're operating you're trying to do something like that, pick an interval out of a range of out of a list, right? Put it in intentionally put the correct answer in the end, put it in the beginning, right? You also want to test what the maximum or minimum products would be. So in the case of max product, 9 9s multiplied together, that would be the highest possible result. See if you can get it. The smallest possible result is 0. See if you can get that. And generally speaking, another good one is if the input is exactly equal to the size of the interval you're looking for. In the case of max product, how that gets interpreted more generally is when you're using loops, you want to test the case where the loop does not actually execute, right? For lists and problems like that, this often means testing an empty list, or some data structure that doesn't actually have any values in it, or one that doesn't generate any values, right? For like a filter that it ends up nothing passes through the filter, right? Those are some types of edge cases that you want to think about. For the juggler example, you guys all remember the juggler problem from the test, right? The conjecture is that if you perform these, floor and exponent operations sufficiently, a sufficient number of times, you will always eventually wind up at 1, which is an interesting conjecture, and one that has not actually been proven, as I stated in the question. But for the purposes of testing the software, see what the behavior is if 1 is given as the starting number. So you need to do 0 intervals. And if there are no specific injunctions against it, you also want to test what are considered invalid inputs. And this is going to be getting more into once we start talking about exceptions. But invalid inputs are a good thing to test. It's good to see what the behavior of your algorithm is if it's getting something that ordinarily it shouldn't, like something beyond the scope of what was considered a valid input. So, in the case of the juggler example, that would probably be something like a negative integer, because it's only supposed to operate on positive integers, just like the Collatz conjecture, which is like one of the classical examples in programming. So, yes, you want to test all this stuff. Test cases, test cases, test cases. And in addition to all of the regular test cases, you also just want to test a few values in the middle, right? The idea is when you have ranges of things that do different things, these values that are sort of nominal values, right? It's also important to see that these nominal values are operating according to what you think they should be. But anyway, that's hopefully enough knowledge of how to write test cases to get you through to second year. So, yes, sample test cases for max product. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. We know that our algorithm originally resulted in this number. However, this is an edge case test. Obviously, like we already did this example, the interval that's being measured here is 1 smaller than the interval that is actually that you should be measuring. You should get a result from the last 12 digits, but you get from the 8 to whatever the other one would be. Yeah, so yeah, essentially. We already showed that example. So when you are generating, and this is going to seem like a common sense thing, but when you are generating your expected result, right? When you're generating the thing that you're comparing your results to, it's important to do that by some mechanism other than the program that you're intended to be testing, right? Again, it's a common sense thing, but how are you verifying that this program is working correctly if you're using the results of this program to verify that this program is correct? It's an epistemological issue. But yeah, that's, kind of neither here nor there. Just use your calculator, like your Casio. It's not always possible to have an independent method. Sometimes things are so sufficiently complex that there's really, like, there's literally nobody else in the world that's doing what you do. See my thesis. And it's not really possible to have that type of an independent method. So, in that case, you can check for consistency. For example, with respect to our max product example, if I, for example, place a 1 at the end of this string, that's not going to affect what the max product is, right? It's still going to be this interval. So, there you go. Still matches up. So that means that the project is correct. However, if the bug was still present, right, adding this shouldn't modify anything. But it does, and it makes the answer correct. That would have been another dead giveaway that we're dealing with an off by 1 error. There you go. So, and just in summary, for those of you who are reading the slides without watching the lectures, in which case, why am I even addressing you? This slide indicates that this 12 should be an 11. There you go. So, we shall dwell briefly on the subject of white box techniques. So, code review is a white box technique. This is where 2 or more developers visually inspect programming code. Typically several times, you make a few passes, and there are a few things that you're looking for. Number 1, programming best practices. So I know things have been kind of loosey-goosey with this course, and my approach to it is very much like, you guys are just learning. You need to have free reign to explore the topics that you're trying to learn, right? Like, you have to be given sufficient intellectual freedom to be able to solidify in your own brain how it is that a person could make their brain think like a computer. So, the object, from my perspective, is to not try to burden you guys with, what programming best practices are, or, when we have a problem, I don't say, and this is the typically accepted solution for this type of problem. You must always name your variables X, Y, and Z. You must always create loops in such and such a manner. I don't do that because it stifles your creativity. And, programming is fundamentally a creative exercise. However, if you work for a company, and that company deals with code, it is very, very probable that your company has some programming best practices. Sometimes this can be naming conventions for things like classes and variables and functions. This is actually pretty common. I have seen coding conventions where the type of the variable is a prefix of the name of the variable, or a suffix of the name of the variable. That way, whenever the variable is used, you always know what type it is. It's a very useful thing, especially in a dynamically typed environment like Python. Although it is a little bit clunky, this is good. Prefixing all of the function names in your code with fn for function, that, it's a convention. These are things that companies may at some point require you to do if you end up working for a company making code. So if your code is under review, that's the sort of thing that they'll be looking at. Generally speaking, algorithmic stuff can also algorithmic best practices can also be checked. There are actually automated tools for some languages which check your code against standard practices or best practices that can be codified. Like there's actually a fair amount of research work with respect to the generation of best practices and the application of best practices. But, generally speaking, the low-hanging fruit when it comes to best practices is things like naming conventions. Anyway, during code review, they may also be looking for potential inefficiencies. So if you're allocating a butt-ton of memory to some process and only using 2 bytes of it, they might say, don't allocate so much memory to this subprocess, you don't need it all, something like that. They might also be looking for common vulnerabilities. An example of a vulnerability that we'll be actually going into in some depth in the coming weeks is what's called a SQL injection attack. This is a thing that it's quite easy. You can tell visually very quickly whether a piece of code is vulnerable to an SQL injection attack. And, they are a problem, so it's good to check for them. As I mentioned, there are code review tools that can help with the process. And, various companies will have various tool packages that they like to use. There are also formal code review methodologies. These code reviews can be very time-consuming and typically will only occur if the code that's under review is in some way essential or safety critical or will cost the company millions of dollars if it goes wrong. So, there are reasons people will do this kind of thing, but it's sort of not typical to have people look at your code and visually inspect it. That's not this is like the Cadillac of testing techniques. Whereas, so this is like the Cadillac. It's expensive and has lots of assurances that may or may not actually be the case. And black box techniques are your reliable Honda that doesn't cost nearly as much and will get you from point A to B reasonably efficiently, but, just doesn't cost enough for some people's taste, I guess. That may be a slightly unfair analogy. So, when you're examining the code, you want to cover a couple of areas. Number one, code coverage. When we design our test cases, are we exercising all of the lines of code? So if you have a bunch of if statements with a bunch of branches, is each branch being tested? Because if a branch isn't being tested, then you don't know if it's correct or not. So you should definitely test each branch. Same with loops. Is the loop ever at any point actually being executed? Good question. Static analysis. So static analysis is actually highly related to my own thesis work. That's where you run an automated tool to find flaws in a program. So if there are some things that you can check in this manner. You can check to see, for example, in C, in the programming language C, you allocate memory and then you deallocate memory when you're finished with it. Python takes care of this for you. It has garbage collection. But in C, you're responsible, you the programmer, are responsible for deallocating all of the memory that you allocate in your C program. You can have static analysis engines which check to make sure that all of the memory which you allocate is then subsequently deallocated. And like, honestly, this again is an area of active research within the software engineering community. And like, you can go to static analysis conferences, or probably more commonly a static analysis you know, talk or set of talks within the context of a larger conference. But, I'm sure there's like a dedicated static analysis conference, because there is for just about everything. But yeah, static analysis, also very cool. So let's talk about debugging. So, up to this point, we have talked primarily about how to expose bugs. We are journalists writing our exposés on bad programs. So, the problem, though, once you have written a test and that test has exposed a bug, how do you fix the bug? Because that's different from finding the bug, right? So, in order to reliably find a bug, you have to have basically, you need to try to do two things. Number one, you need a test case that reliably fails. So you need to be able to reproduce the error. Sometimes on online bug reporting tools, like sometimes with a software project, people report tools or people report bugs to people who are making tools. You can do this with GitHub, I'm pretty sure. And also, for whatever reason, the video game Dwarf Fortress springs to mind, because that also had a bug reporting tool, because the development for that game is kind of weird, because the guy who developed it never actually put it up for sale or anything, and yet the thing has had like continual support for 10 years. I don't know if it's still going on, but it showed no signs of stopping when I stopped paying attention to it. But that was like I don't think I've seen I don't think I've downloaded Dwarf Fortress in like 6 or 7 years or something like that. But anyway, so in a bug report, sometimes people respond to your bug report by saying could not reproduce. This means that they could not find a ooh, Dwarf Fortress Premium is coming to Steam. Very cool. So they're almost finally finished it then. Ha! Amazing. So, if the person who receives the bug report can't actually reproduce the bug, they can't fix it. So they will put in the response to the bug report, could not reproduce. So once you have a test case that fails reliably, you need to try to understand the internal state of the program. There are a number of ways to be able to do this. One of the most basic ways of doing this is just to embed print statements, or whatever your language's equivalent of print statements are, into the program itself. Have the program print out what the relevant variables are as it's executing. Yes. So this is what I did when I had it tell me what I was through each iteration. I was able to tell that I did not reach the value that it should, and that was causing an error, because I asked the program to reveal its internal state. Goodness, yes. If anybody wishes to lose months of their life to a video game, I recommend taking a look at Dwarf Fortress. It's very cool. It's exceptionally complex, but it is done entirely in ASCII art. Very cool. I will leave that as an exercise for the viewer. So that's approach number one. Very good approach. Approach number two is to use a debugger to step through the program. So debuggers are specific software tools which are designed to inspect source code and the internal state of a program as it is running. So the idea is you can stop the execution of a program, look at what the internal state of that program is doing, and my goodness, I'm gonna have to look. I'm gonna have to check that one out. Yes, I am a fan of 4X games. 4X is like that's for me. That's like my security blanket. I've been really liking Stellaris. If anybody has played Stellaris, it's also a space game. Anyway, should never mention video games. So you have your program, you can execute it. And of course, the problem with sort of imagining that you can just, like the slot reels in the old Pokemon game, you can just stop the code, at the point you want the code to stop by just pressing the A button or something. That's of course ridiculous because your Python scripts will be executing in very small fractions of a second. You would not, even if you pressed it immediately after you pressed the start button, the program would probably still have finished by the time that second button press occurred. So what you can do is you can set what are called breakpoints. They are sometimes even indicated by stop signs in the debuggers that they are in. A breakpoint is essentially you designate a point at which the program execution stops, and then that allows you to pause the program and inspect what the code is doing, what the state is doing at that particular point in time, and you could even from there step through the execution of individual statements in order to see how the state is changing. Sword of the Stars. That sounds like a cool name. So, idle is a thing. It's an integrated development environment for Python. It's built in, so you can run it by typing idle3. Let me see if I've got it. Idle. How about Anaconda? Navigator. You got me some idle, Anaconda Navigator? Boink. Anywho, this is what it looks like. Get out of there, you. So you've got the code in one pane. You've got the Python shell in another. And then you've got this debugger control. It has various things you can do, like go, step, quit, etc. And it displays to you what the values of each of your local variables are, which is pretty dang useful. Oh, cool. There you go. I don't know if Anaconda will just give me it. Give me idle. Give me something. Can I do it in a PowerShell prompt? I wonder. You guys are probably laughing at me. Anyway. I just want to show you guys how it works. But yeah, so generally speaking, there's also I do not have it installed on my local installation of Jupyter, but there's a Jupyter. Ah, there we go. idle3. Nope. Run idle 3? Nope. Python? Python works. Yeah. Of course it does. So, anyway. Get out of there, you. Anyway, it's super cool. If you'd like to play around with some of this stuff, there is a notebook called Jupyter Superpowers, which was done by a fabulous character by the name of Eric, who used to be a TA for this class, and he shows you how to get a debugger embedded right in your Jupyter notebook that you might even be using for assignments and stuff, which is really cool. It's called Pixie Debugger, which I believe you can just kind of look it up if you're interested. So, we have talked about debugging. We are now talking about exceptions. We're going to be exceptional, folks. So, let us suppose we have a hypothetical situation in which we wish to create a function that returns the maximum number in a list. You might say, well, why wouldn't you just use max? And that would be one answer and one way to do this solution, but not the one that we are talking about today. So, the question is, what should the function return if you give it an empty list? So, there are a few options. You could have it give you 0. That might not be a great idea. Number one, 0 wasn't actually in the list because the list didn't contain anything. And number two, you could even have lists that return things like 0 might actually be a legitimate response, right? Like you can imagine if you have a list that's filled with negative numbers and 1, 0, 0 would be the maximum of that list. And if that 0 was absent, the maximum would be even less than that. So the selection of 0 is extremely arbitrary. Infinity? No, maybe. Not a number? NaN? Possibly. Some languages support non-numbers. How about the Boolean false? Well, as anybody who knows what the underlying binary representations of Boolean values would tell you, that's actually not too dissimilar from just returning 0, because if you cast 0, the integer, if you cast false as an integer, you get that as a Boolean, or as an integer, I'm pretty sure. Int false, yeah, and int true. There you go. Int true is 1 and false is 0. And I think that also if you have any number that is not 1, that's also false, but that might be, nope, sorry. It's every number that isn't 0 is true. Ta-da! So, boop. I'm just going to refresh chat again. I don't trust it now that it stopped updating for me once. So, false is not you could return false. However, it's not necessarily sufficiently distinct from 0 to gum up the works of things that are assuming you're getting 0 incorrectly in the case of a bad input. The other thing is, what outputting false requires what it requires of the users who use your function is it requires them to check for false each time they use your function, right? Because, we've all been, up to this point, we've been dealing with these very concrete cases where all of the lists that have been going into functions have been literals or things that we know the values of. But very, 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 very often in programs, when you write a program, you don't necessarily have a concrete idea of what you're passing through, right? You don't necessarily know what the list you're giving this function looks like. It may very well contain empty lists. Like your inputs may very well have an empty list in them. So this may be a thing you actually have to deal with. So if your function returns false on failure, the user of your function is going to have to check that everywhere. And this kind of breaks down the idea of modularity. Generally speaking, your function should not come with strings attached, right? Your function should not come with, oh, but if you don't, check at this with an if statement to make sure that you didn't get a false return value, then you might end up in badness. So we have an alternative way of solving these problems. In this slide, we're just further illustrating the point that I was beating senseless in the previous slide. So, yes, if, for example, if you're calculating a bound, if min or max returned false, the question is, what is false minus false? And the answer to that is 0, which doesn't necessarily make any sense, right? So, the thing that you can do, and getting ahead of the slides again. To fix that problem, you'd have to introduce all these if statements. It's really mucky and messy, and nobody wants to do that. Basically, you would have to introduce all of these if statements to keep passing the falses up the chain, which, is just a lot of bookkeeping after a while. So, a similar question: what happens if you pass a string into integer conversion? Does it give you 0? Well, let's see. Pass a string into integer conversion, incidentally, which is not numeric characters, right? Because if you convert a string that is numeric characters, that just works. But if you try to convert to integer something like potato, you get a value error. And this is just a very long wind-up to us introducing the concept that errors are useful. My goodness. Yes, we get an error. Yes, so here's the question. This is just fun. Int input, enter a number. No. Error. So there you go. This is maybe we'll come back to this running example. Make it a running example. Exceptions. Exceptions are a thing that we're going to talk about after the break. Cha-cha-cha-cha. Kablamo! I'm back! A minute early. Ha! Thought you had it all figured out. But then the professor shows up 1 minute early. He's probably gonna just, you know, not start until actually 7:30 though. I am seriously considering the fact that we may not get through, well, no, pardon me. We will get through this slide set. It may be a matter of we have more time than we need to cover it all. But that's okay, we can just do a couple of examples or something. But so a thing that you may not have known about the new slide sets, if you click on the buttons up, these aren't just indicators, these are actually links. So you can actually navigate according to these little these things at the top here, which is quite cool. I think it's neat anyway, but then again, I did commission these, so it would be pretty bad if I thought they were garbage. Anyway, there's a kitten approacheth. Boink. Hello. Do you want to be on live stream again? Whoop. Here we are. Say hello to the internet again. She's like, you do this to me every Wednesday and Monday. What is going on? Oh, hello. Is it okay? We're talking about exceptions. There we go. So, exceptions are a mechanism. Oh, I see what happened. All right. A glass of... Okay, so she knocked over my glass of water, but not just now. During the break, she came in, knocked over my glass of water, left, now is walking through the water and getting it everywhere. But fortunately, it's just water. Could we also talk about programming future stuff like machine learning with extra time? Well, we actually have a whole slide deck on machine learning coming up at the end of the course. But yeah, we can talk about stuff. I will answer any questions. So let's get through this. So exceptions. Exceptions are how Python chooses to deal with situations where it tries to execute a statement that isn't well defined or violates some condition. So, basically, if an error occurs, where an error is defined as something unexpected, unexpected by the program, not by you, then an exception is raised. Raise is an important keyword. This typically interrupts the normal flow of the program's execution. So you will all know this. Once the program hits an error, it stops at that error, shows you the error, and then just sort of stubbornly crosses its arms and says, well, I'm not doing anything else because you obviously don't know what you're doing. So I don't know what I'm doing. That's what the program is saying. So there are two ways that this can go down. Number one, you can handle the exception, and we're going to learn how to do this. You can write a handler which attempts to catch exceptions and then recover from them. Or the exception can be unhandled. Unhandled exceptions are the ones that crash programs. If the exception is handled, then it doesn't crash the program. Instead, it executes some other code. So, as you can see, from our code that we were running in Jupyter, which this is basically the same thing, if you ask for a number to be entered, and you enter a number, then it's fine. If, however, you ask to enter a number, and you refuse, you get a value error. This is cool. Boop. So let's try it with an exception handler. So the manner in which you write an exception handler is you write try, and you indent everything. You use a colon and you indent the same way as if you were doing an if statement. A try is kind of an implicit, let's run this and see if an exception happens, right? If an exception happens, it interrupts the execution of the code that's inside of the try block, and then it runs whatever code you print, or whatever code you put in the except clause. So the except clause can have various specific errors denoted. In this particular case, if we have a value error, then we are doing this thing. You can actually chain together multiple types of errors here. Like you can have except value error, except index error, except some other error. You can have multiple of them the same way that you would have an if-else block, right? This code will execute if an error occurs during the execution of the stuff that's in the try block. So let's take a look. This seems like it might be this S seems out of place. It might be a typo. So try, enter a number, accept, value error, print. Fine. I didn't really want you to give me a number anyways. Enter a number, 9. There you go. Of course, in order to actually see the output, you have to bind it to some variable. There you go. And if you refuse, notice, all right, I'm going to change the variable name, and I'll show you something interesting. Notice we get a name error now. So you should be careful about this type of thing. If an error occurs during the execution of a statement inside of the try block, that whole statement can be considered to have not happened. This includes the definition of the y variable that occurs inside of this try block. So if we, in fact, pass through this try block, it hits this exception, and you get a value error, and then you require the y later on, which presumably you will, because otherwise why would you have asked for it? This isn't going to exist when you ask for it, because this piece of code right here, it's like it never happened. So there are a couple of ways to get around this. The first way is to assign some default value for y, or initialize the variable. So, generally speaking, somebody can make me a t-shirt that says, generally speaking, it's a bad idea to initialize a variable inside of a try block. That can be a t-shirt. Otherwise, another way of handling this is to put any code that requires the variable inside of the try block. So this means that the code will only print y in the case where y is determined. And in cases, and I'm going to have to change the variable name again just because of the persistence here. In the case where the exception is hit, Nothing past that exception executes, so Z is never attempted to be printed, which means that it never is not, it's never, you're never attempting access of a thing that doesn't exist, right? So that's just a little, that's a fairly important point when you're actually trying to use these things. So this is how you handle exceptions. And a couple of interesting notes. You can specify the error name. If you do not, then it handles all exceptions. So, generally speaking, except without specifying which types of errors you're having an except clause with, that might be considered somewhat safer, because if something very strange happens, an error that you did not predict, for example, you can catch that with an except block. You don't have to actually predict the error type. That's important. You don't actually have to predict the error type. So, just to review, we put the code that might cause an exception inside of the try block, and we use one or more except blocks to specify what the code should do if the code causes one of these exceptions. Sometimes it's raise another exception, but, you know, neither here nor there. So, here are some common types of exceptions. Whoop. Index error. So, when you are trying to access an index that is out of bounds for a particular list or string or whatever, you will get an index error. So I have a question. Albert asks, can you have multiple except blocks for different errors? Yes, you can. I can demonstrate. Let me see here. Let me think. Yes, zero division error. That shall do. So if we like print 10 over Z, right? So I don't know if I've actually talked about this yet, and this may not be intuitive to some people, but computers can't divide by zero. Like, if you ask a CPU to divide by zero, the actual, like, at a circuit level, the computer will just go and do ridiculous error state things and just not operate correctly. So generally speaking, no computer can divide anything by the number 0. In our conventional mathematics, if you enter, if you perform division of something by 0, you get infinity. Infinity cannot be represented inside of a computer unless you have like a specific infinity thing. Like, I'm being a little bit overly simplistic here. There are environments in which you can perform zero division error, right? But the like MATLAB, for example, I think you can do that sort of thing in. But generally speaking, in Python, if you attempt a zero division, you will get a problem. So if we enter nothing, we get that error. If we enter some value, we get essentially, we can get its inverse. I'm going to change that to inverse. And if we enter 0, you can see that we are now executing the branch with the 0 error rather than the other one. Yes. The comments the comment, because of 1MD3, I don't actually remember what I said. So I can't answer that question. Ooh, statistics. Cool, we peaked about here at 70. Oh. Oh. Yes. Oh, yes. Yes, that totally was. That was a reference to Star Wars, the second one, which is actually the fifth one. I think that one, Attack of the Clones, something like that. The one where he's trying to buy death sticks. Yes. That was a Star Wars reference, for those of you who are hoping it was. So anyway, index errors. When you try to address things outside of, if you're trying to get at an index that doesn't exist, index error. If you're trying to perform an operation on a, come here, you can't play with my headphone cords. Naughty kitten is playing with headphone cords. If you try to perform an operation on a object that is not appropriately typed, then you'll get a type error. A good example of this is if you want, like, we know that with lists, multiplication is defined, right? But addition is not. So what does it mean to add 6 to this? It's like, well, this is a concatenation operator, but this is not a list. You can't just concatenate something to a list that's not a list. The big brain way of solving that is to just make a list with one element there. But that is a type error, and that's how you create one. Value errors, that's the type of thing that we've been talking about so far. A value error when a function or operator is applied to an object of the right type, but it's otherwise inappropriate. I may ask you to create value errors on like the test and stuff, because that's an easy one. Oh, yeah, I should just mention, all of this exception stuff is like super easy to work into test questions. So ordinarily, I don't necessarily have like the exceptions question on a test, but it's kind of just sprinkled in among the other question types. Now, that being said, on this upcoming test, like, this is like one of 3 topics, so there's probably going to be a specific exception question. But, you know, with respect to like the exam, you can probably expect some exception skullduggery to occur within the context of a question that doesn't really have much to do with exceptions. File IO is a good example. Like, if you enter the wrong file name, throw an exception. Not implemented error. This is the error for lazy people. When a function has not been implemented, have it raise a not implemented error. Generally speaking, don't expect many marks if you do that, unless you've been asked to. Recursion error, when the maximum recursion depth has been exceeded, so you now know how to catch a recursive function that exceeds its recursion depth. That might be useful. Runtime error, when some error occurred that isn't classified elsewhere, so the other error is a runtime error, and the zero division error, which we've already addressed. So those are your common error types. And wow, we are through this lecture slide way, way early. Oh, but where's the raise? There should be a... Did I miss the bit where we talk about raise? Good Lord. Okay. I think there might be like one slide missing from here. So I'm going to talk to the TAs and see if we can't have that slide inserted, even if it doesn't exist. Assertions. We'll talk about assertions. You may have noticed that if you've been like looking at some of the test cases that have been occurring in the assignments and such, that sometimes we use assertions. Assertions are actually the way that the autograder determines whether or not the code that you've executed works or not. It's just a Boolean test. If this Boolean expression returns true, then the assertion passes through with no... Did I pass it? I'll come back to it. 4 from the end? Okay, thank you. Thank you. If the assertion, if the thing you're asserting is true, then execution passes through the assertion with no effect on the code. If the assertion is false, then the program raises an assertion error, and that is useful. It's useful for defensive programming. It's a way of requiring your variables to be of particular values. It's also the manner in which the autograder works. If the autograder, basically the autograder determines that you have not correctly completed a test cell, or your program doesn't work for the test in the cell, by checking to see if an exception is raised during that test, right? And the exception can be one that your code creates, or it could be one that the assertion statement in that test case creates. So, assertions. Cool. 4 back from the end, you say. Ah, yes, raising exceptions. Thank you very much. Gotcha. Cool. So, the final tool in your toolkit. You can raise exceptions in your code using the raise keyword. So, if you want, for example, in this particular case, raise type error, except type error, print, well, nothing else was wrong, so I broke it anyway. There you go. You can see that this error was raised and it got caught by this except statement. You can just, if you want, I don't know why you would, but if you want to just raise a value error, you can do that. It just works. Generally speaking, within the context of assignment question or something like that, it'll be something like if, n is less than 0, raise value error, or there'll be some like my throat's just a little dry. There will be some condition upon which you are required to raise an error. But that's how you do it. This is how you create exceptions. This is how you become exceptional, so to speak. So yeah, that is... Good Lord, it's only 7:53, and we are through all of the material here. If this were an in-person class, I would be inclined to start on the next set of slides. But given that everything is like so nicely segmented and the lectures are like the way that I've been doing the live streams is each lecture is a topic, and I don't think it's a good idea to get away from that because, it'll just confuse people probably. So yeah, I guess this becomes Q&A time with the prof and the kitten. AMA, ask me anything. Don't ask me what the exam questions are because I haven't written them yet. So what do you guys want to know about machine learning? Be more specific, man. That's a pretty big topic. I mean, I can tell you that machine learning is a very highly active area of research. I think a conversation on future courses will be nice as well. Life science to stake in. Well, I'm glad you're enjoying the content. Some suggestions on future courses that build off this course. Favorite Jedi. Oh. Favorite Jedi. I mean, I don't know. Maybe I'll be maybe I will be considered a normie and a horrible pleb for saying this, but I kind of like Luke Skywalker. And by Luke Skywalker, I mean like from the old movies, not new suspicious liquids Luke Skywalker, if that anybody who knows that reference will get it. Yeah, okay. So I got a couple of requests. So let's talk courses. Let's do this. So let me just pull up the registrar's website and we can take a look. Registrar. My goodness. Registrar. Thank you. Undergraduate calendar. So, in general, that's true. Qui-Gon Jinn is pretty. I did like him, but I couldn't tell how much of him was me liking him or me liking Liam Neeson. Whereas Mark Hamill, back in the original, I know that he's actually done like some really good acting work since those movies, but like some of it is so rough, man. So it has to be the character that I like rather than the actor. Mark Hamill's good, but like some of those early scenes, they were rough, man. I'm thinking about you, scene when you learn that your father is Darth Vader. Yes, I agree. You would just slap. What do you think about? You're thinking about the dark side again, Anakin. How many times have I told you? Don't talk to men in suspicious black robes. Good lord. Anyway, course listings. Let's take a look at everything that the computer science faculty has to offer. Yes, I know. The cats. Yeah, I agree. Like, Mark Hamill has, like, I think he's actually a better voice actor than he is a live action actor by a country mile. But you know, also I think he's perfectly cast as villains. You know, but anyway. So anyway, so let's take a look here. 1MD3, that's a thing we're currently doing. We've got, in terms of first-year courses, there's Introduction to Computational Thinking, Inquiry into the Ideas, Methods of Computer Science, the science underlying our computational universe. Topics include what computers can do and cannot do, the internet and searches. Seems like a bird course, maybe. I don't know. Wait, is that 1JC3? Is that that can't be is that the Haskell course? Because like that looks like it has nothing to do with Haskell. Oh well. Okay. Computer science practice and experience basic concepts. This is cool stuff. This is more hands-on. As far as I'm aware, wait, maybe I'm getting these reversed. 1JC3 might be the it's like Linux stuff, like learning how to do like write shell scripts and stuff like that, and learn what repos are and do, maybe stuff like that. One of these courses is that, and one of them is the Haskell course. But in either event, you guys asked about upper year level courses. So number 1, data structures and algorithms. Highly recommend. Basic data structures: stacks, queues, hash tables, and binary trees. Searching and sorting, graph representations, and algorithms, including minimum spanning trees, traversals, shortest paths, introduction to algorithmic design strategies, correctness, and performance analysis. Yes, 1JC3 is the Haskell course. Data structures and algorithms. This is the course that will turn you into a wizard. And I say that like meaningfully. Like if you want to know like this, like data structures and algorithms, I would consider that like core curriculum for the whole frigging degree, if that makes sense. However, I think it's got it's got discrete mathematics with applications as a prerequisite, so you would have to do that first. I would say it's worth it. Functions, relations, and sets, the language of predicate logic and propositional logic, proof techniques, counting principles, induction, recursion, discrete probability graphs, and their applications to computing. Math course, but if you like the logic and the stuff that we're doing, then you would enjoy it. So, did I do my undergraduate degree at McMaster? I did, in fact. I did my undergrad degree in mechatronics. I'm not actually a COMPSCI student. I didn't go through the program I'm currently teaching, which is perhaps to my disadvantage. But, I was a Tron! Mechatronics engineering. That's electronics and mechanical systems and all kinds of stuff like that. But with a heavy emphasis on software, as it is sort of done by the software faculty, and that's sort of where I ended up doing my grad work. So, Konstantinos, are you teaching any courses this fall that I could take? I really enjoyed this course so far. Well, thank you very much. I appreciate it. It's always nice to know that somebody's having fun except me. I always have fun, but whether other people do too, that's just icing on the cake. But so I'm a sessional, right? Which means that I'm employed for contract work. how it works with sessionals is you apply to the pool of sessional positions that are open for a particular semester, and if there's an application process, and if you get that contract, then if you get it twice in a row, then you get first right of refusal for 2 more goes round. So with respect to my whether or not I'm going to be teaching anything in the fall, I think that generally speaking, and like, don't quote me on this might not be actually the case, but I believe that generally speaking, the courses that I hire sessionals for in the fall semester tend to be the 3rd and 4th year courses. Not maybe a 2nd year course, but I certainly wouldn't be put on anything like data structures and algorithms. That's like prime territory, you know? Are all these courses available to all students, or would you have to be in COMPSCI for it? I'm not sure. I think that if you're going to do a minor in COMPSCI, then they would let you take whatever courses you wanted. I mean, I don't know. As long as you got the prerequisites, what's the problem, right? But then again, I'm not the registrar. Probably some of these questions are better directed to someone who knows what they're talking about. I'm pretty sure that as long as you have the prerequisites and you can convince as long as you fill out the form. My impression of like people who fill out the could I please be accepted into this class form is that generally speaking, people like the default instinct is to accept people into classes unless they are like seriously and obviously not going to succeed in them. But yeah, I think as long as you have the prerequisites, you'll be okay. And if you notice, so the prerequisite for this guy is either Math 1ZC3 or Math 1BO3, or registration in the Honors Computer Science as a 2nd degree program. So if you're registered in computer science, you don't need to have taken these. But I don't know, like, are these math courses seem like they might be standard fare for science students, so maybe you would be fine. But yeah, generally speaking, I think they're pretty. I don't know how many units you need to minor. Again, that would probably be better directed towards your faculty advisor. So anyway, with respect to my position as a sessional, it kind of depends. It depends. There are some really favorable prospects coming up for me for full-time work, possibly at other institutions, and given that my thesis is basically in the waiting for people to read stuff phase of things, and I'm very, very near to completion, time to get a full-time position if I can hack it. That's the thing, is it's actually reasonably difficult for a sessional to actually, break through that barrier and become a full-time person. If I get a full-time job for the fall, obviously I won't be teaching anything here at Mac. I do have some courses. I have a course lined up at Mohawk College that I would possibly be teaching as well. So I do have a prior commitment for the fall semester. We'll see how things go. It's still pretty early to tell, but generally speaking, like, if I don't have, I certainly have first right of refusal on the next offering of this course, so I'll probably teach that. But with respect to 2nd year courses, I don't know. Maybe you can petition the department. Tell my department to hire me full-time, and then you can have me for as many courses as you want. How's that for a deal? Some courses state that they are for COMPSCI majors only. Most life sciences students stop after Math 1 LS3. Well, you might need to take another math course. It's entirely possible. Let's see if we can find some of these. Principles of programming. Prerequisites. I think 2SO3, like, that looks like the most, like, directly on from this course offering in this list. I think I've done this before. Pardon me, from my memory of having similar conversations with other students, 2SO3, I believe, is like your direct follow-on from 1MD3 as closely as possible. So it would cover, many similar things, but at a more advanced level. Like, we're not really getting into records or dynamic structures or anything like that. But yes, you can see a lot of the stuff is carried over. This would be a cool one. Unix and shell programming, makefiles, version control, assembly basics, translating high-level language into assembly, parameter passing, arrays, recursion, compiling, debugging, profiling, and software optimizations. If you really want to get into the low-level details, like the real nuts and bolts, 2XA3. If the cats come with it as well, we'll get it done. So let it be written, so let it be done. I have to make over 16K a semester, though, to make it worth my while. Computer architecture, I don't know, that's kind of, well, yeah, like logic gates and stuff, that's cool. It's basically, that seems a lot like, that unit we did last on Monday. This seems like the course version. Discrete math with applications. Predicate logic, ooh. Predicate logic and formal proofs, grammar and automata, modular arithmetic, and their applications to computing. So this is actually, like, highly related to the type of thesis work that I do. Predicate logic and formal proofs, like, that's like the high math of computer sciences. Any courses about Excel and databases? Well, yes. However, it's a third-year course. It seems that its prerequisite is 2DM3, which one is that again? Discrete math with applications 1. So if you do that one, you should be able to do the databases course. Data modeling, integrity constraints, principles and design of relational databases, relational algebra, SQL, query processing, transactions, concurrency, control, recovery, security, and data storage. Yes. If you want to learn databases, like a goal course, because you would have to take some prerequisites, would be 3DB3. They called it DB for databases. Cha-cha. Interesting, they've got a third-year course for functional programming, yet they teach Haskell in first year. Wah, wah, wah. They probably do, like, the monad. Yeah, programming with monads. So this would be like your, okay, now we're going to really teach you how to use Haskell type course. Programming languages can be a really good course depending on who's teaching it. Sometimes programming languages courses are like a survey course of a large number of different programming languages across a number of different paradigms. So you get, some of this, some of that. Gives you a very broad, it's almost like a liberal arts education with respect to programming. So that's kind of cool. Fourth year courses. I'm not sure if there's any point in talking about them. Because, you know, I'm not sure, like, if there's anything, advanced databases. If there's anything, if there's anything they restrict people's access to, it's going to be the fourth year courses, I feel. Probably second year courses they'd let most people into. But anyway, so that's a sort of a discussion of courses that you might take in the future. Just in summary, if they allow access to it, 2DM3 is a gate to many of the good and interesting courses that you would take. Like, they're all good, they're all interesting, but certain things like the data structures and algorithms course, or the databases course that you were interested in, Marvin, these are, you're going to want to get in through 2DM3, which will require you to have a math prereq, so to speak. GG no re. Oh. Which one is object-oriented programming? Good question. Huh. Yeah, 2ME3 is like the lecture we just had as a whole course. Oh, I just instantly fell in love with this course because it has the term Turing thesis in the description. Ooh, yeah, okay. So once you've taken, once all of you have taken data structures and algorithms, then take this course, because that's like, oh, I'm salivating just thinking about it. I don't know, it doesn't look like there's a specific object-oriented course. Probably object-oriented is, like, so integral to a lot of the stuff that you'll be doing that it's never really, like, explicitly covered over the context of an entire course. That's okay. We're going to do our best here in 1MD3 to cover that that one. But, yeah, I don't know if they have a specific course on object orienting. It seems like it might be a bit of an oversight, to be honest with you. The dark side of the force, the pathway to many abilities, some considered to be unnatural. Is it possible to learn these abilities? Not without Nick Bohr. Yes. So, anyway, we have a couple of minutes left, which there is like a general request for me to waffle on about machine learning. So I will preface this by saying I am not a machine learning guy. There are specific machine learning guys. There are people who machine learning is their whole thing. I'm not one of them. I'm more of a formal methods and logic guy. I'm more in the functional programming and the, wherever that thing was that had logic in it. That's where I am. So, machine learning. It's like lots of people think that machine learning is like the singularity, like the coming of the singularity, the degree to which this is the case, I think, has been somewhat overstated. What machine learning is statistical analysis. Fundamentally, machine learning is statistical analysis over large data sets. from a mathematical standpoint, this is what you do. You collect a literal butt ton of data, right? You then throw this algorithm at it and say, okay, I need you to synthesize for me a model of what's going on with this data. And the computer is like, oh, well, okay, I will try all of my different types of analysis to attempt to discern what is going on with this data. And, regression analysis, like a linear regression or a polynomial regression or something like that, that's a machine learning technique. You also have things called things like clustering analysis, which determines groupings of objects, classifications of objects. It turns out that the problem of classification is a really hard one. They didn't think that this was going to be a really hard problem, but and the argument could be made that once you teach a computer how to abstract, that is, how to categorize, you're further along the road to what you might consider real intelligence, artificial intelligence. However, the thing that most people are concerned about with respect to artificial intelligence is the thing that like Elon Musk talks about, right? This, you're going to wake up and suddenly overnight the computer will have, like the computers will have accomplished 10,000 human years of development in the space of 10 hours, and will have arrived at a point of such overwhelming power and intelligence that they will overnight become, a new force to contend with on the world stage. And, we only hope that in all of their explorations of intelligence, they somehow developed a code of moral ethics, right? So it's really hard to get there from statistical analysis, right? Although people are working on the type of machine self-improvement, like this machine self-iteration, people are working on that type of thing, perhaps somewhat unethically. We'll see. That the deal is that the machine learning that is like presently applicable, and the thing that most people are like the thing that most people are referring to but don't realize that they are referring to it a lot of the time when they use the term machine learning, is just simply statistical analysis over large data sets. Like, for example, yeah, I mean, don't get me wrong, Elon Musk is he's a cool dude, I've been meaning to watch that that podcast he did with Joe Rogan like 2 weeks ago. That's on my to watch list. But I don't agree with him on everything. He's a very interesting mind. He's got an interesting approach to things, but like a lot of the stuff he talks about is really sci-fi, But that's cool, Anyway, so what's tricky about machine learning is that the computers can develop models that are superior to human analysis, right? This can be used for good or evil. Just like all scientific advances, the scientific advance itself is a morally neutral thing, right? It's neither good nor bad. It is the application of that advance that determines, whether it is, whether it's a good or a bad thing. Like nuclear power, good when it's nuclear power, like nuclear, fission technology. It's good when it's a nuclear power plant. It's bad when it's a nuclear bomb. Machine learning. It's good when it's allowing ultra fine analysis of MRI scans, which is totally a thing. you know, a machine learning system can detect things in an MRI scan that a human being just simply lacks the sensitivity to be able to pick up. But it's bad when, like, and this is somewhat anecdotal. It's bad when Facebook sends you all kinds of ads for divorce lawyers about 4 months into a new marriage, right? So, like, you know, and you run into all of these sort of traditional issues with statistics and statistical analysis, which is, while statistics can predict a trend, not only does correlation not imply causation, but you cannot determine the state of any particular person to which your statistical analysis applies just by the mere fact of your statistical analysis. It's not possible to tell how intelligent a person is from, broad, um, like, regional IQ assessments or whatever. Yeah, there's only a fine line between fertilizer and explosive. Yes. Oh my goodness. Yeah. Like, and I realize I'm cutting into your break and you guys have to get off to your tutorials really quick, but, like, science fiction is an interesting genre because the whole damn genre has essentially one thesis. It has essentially one premise, and that premise was established by the arguably the first science fiction novel, which was Frankenstein, Mary Shelley's Frankenstein. We can create all kinds of interesting things through the use of technology. But that is not, like, the creation of something the creation of new technology is not a morally good act. And because it's not a morally good act, you cannot assume that because a new technology exists, that the human race will be improved by it, right? You have to assume that it requires morally conscious, well-acting, good-acting human a human agency in order to take the raw material of scientific advance and create something good from it, right? Because it can be equally used for evil. Like, you know, chemical advances in chemistry allowed us the development of mustard gas, right? But mustard gas is a terrible, horrible thing that human beings have decided is a thing that a human being should a thing that you should never be allowed to use it on another human, right? Like, but and science fiction is interesting because through almost the entire history of science fiction, it's been an exploration of this theme. And I think that the reason that people still participate in science fiction as a genre is because it's still a relevant thing to talk about in our modern age. In fact, like, the more technology accelerates at this accelerating pace, the more yeah, the more questions we have about it. And it's correct to have questions about the science. Is this a good thing or a bad thing? Not to be too topical, and not to endorse any conspiracy theories or anything like that. But maybe experimentation with viruses is not something that should be done. It's hard to tell. Because it's scientifically valid, right? But whether or not it's a good thing morally, I think that really highly depends. It depends on how things play out. But at any rate, with respect to machine learning, it's just like every other. It's just like every other scientific advance. It's actually not too difficult to understand the principles of it, which we'll be doing in a future video. Or yeah, a future video. I'm now referring to them as videos instead of lectures. Good God! Actually, in the last one. So, with respect to that, machine learning is a tool. It can be used for good. It could be used for ill. It depends on who's using it. What it certainly will have the effect of, which pretty much every other technology has had this effect, it will disproportionately benefit people of higher cognitive ability, right? People who can set up a machine learning system will be able to take advantage of the technology in ways that people who, lack the ability to code it even won't be able to, right? There will be, it seems like the marketing people are always really quick to jump on these sorts of things, and I'm not sure that that's a force for good in humanity. And like that's already happening very clearly. But not all the applications are bad, and I don't think that it's gonna, put all human beings out of work by making human intelligence redundant. Because human beings are fundamentally more than just engines for statistical analysis. But that's kind of my personal view on it. Maybe this has been interesting to you. At any rate, if I keep you any longer, then I really am stealing you away from your tutorials, which I should probably not do, seeing as the tutorials are for my course. I wouldn't mind if it was someone else's course I was stealing you away from. But anyway, thank you very much for your time and attention. My wife has just made fresh banana bread, so I'm going to go eat that. Have a nice evening, and